Imagine a machine that only needs 200 seconds, just over 3 minutes, to solve a problem that would take the world's second most powerful computer 10,000 years to figure out.
For decades, quantum computing promised to redefine the future, but its biggest breakthroughs seemed years away. Then Google unveiled a development that shattered expectations and stunned the scientific community.
The tech giant said on Wednesday that it's achieved a breakthrough in computer research called quantum supremacy. While traditional computing relies on bits, quantum computing uses quantum bits or qubits, can be both 1 and 0 at the same time.
What once seemed impossible suddenly became reality, raising urgent questions about cybersecurity, artificial intelligence, and human innovation. Is this the beginning of a revolutionary new era? Or has Google crossed a threshold humanity wasn't prepared for? The truth may be even more astonishing and unsettling than anyone imagined. The breakthrough nobody could verify. On October 23, 2019, Google stunned the world with a bold announcement that sounded like something straight out of science fiction. The company claimed that its quantum computer had completed a calculation in just 200 seconds. A task it said the world's fastest supercomputer would need an astonishing 10,000 years to finish. The experiment itself was known as random circuit sampling, but the phrase that captured global attention was far more dramatic: quantum supremacy. It was presented as the moment when a quantum machine had finally done something no ordinary computer could realistically achieve. At the center of this historic claim was Google's quantum processor called Sycamore. It contained 53 superconducting qubits arranged in a carefully designed network. To function properly, the processor had to be cooled to around 10 millikelvin, only a tiny fraction of a degree above absolute zero. That made it hundreds of times colder than the coldest natural places in outer space. Under these extreme conditions, Sycamore performed a complex series of random quantum operations and generated an enormous collection of outputs. According to Google, completing this task in just over 3 minutes proved that quantum computing had entered an entirely new era. The announcement dominated headlines around the world. But behind the excitement was a difficult scientific question that few people outside the research community fully understood. The result produced by Sycamore was not a simple answer, like solving an equation or finding a specific number. Instead, it created a huge statistical pattern made up of countless possible outcomes. Here was the problem. If the task was truly impossible for a classical computer to complete, then how could anyone independently confirm that Google's machine had actually produced the correct result? Without another computer capable of checking the answer, the scientific community had little choice but to trust Google's analysis. And in science, trust alone is never considered the same as proof. That uncertainty quickly sparked debate. Only weeks after Google's announcement, researchers at IBM argued that the comparison had been exaggerated. They suggested that with a smarter way of storing and processing the data, the Summit supercomputer could complete the same calculation in roughly 2.5 days, not 10,000 years. While that was still much slower than Sycamore's 200 seconds, it dramatically reduced the gap that had made the achievement seem almost unbelievable. As the years passed, the story became even more interesting. Scientists continued developing faster and more efficient classical algorithms, repeatedly shrinking the advantage that quantum computers had claimed. Similar announcements from other research groups, including China's highly publicized boson sampling experiments, followed the same pattern. Massive performance claims grabbed headlines, only to be challenged later by clever improvements in classical computing. The lesson became increasingly clear. In quantum computing, an extraordinary result is only as strong as the evidence supporting it. If a breakthrough cannot be independently verified, it remains less a final victory and more an open challenge, waiting for someone determined enough to prove, refine, or even overturn it. But was this achievement able to supersede others from all over the world? What was the final hit that forced the world to bow? Let's find out. Google's biggest quantum breakthrough yet. Google's Quantum Echoes breakthrough is far more than another impressive laboratory experiment. Many experts now see it as one of the most important milestones in the worldwide race to build practical quantum computers. Across the globe, governments, universities, and some of the world's largest technology companies are investing billions of dollars into quantum research, convinced that whoever succeeds first could reshape the future of science and technology. The promise is enormous. Powerful quantum computers could one day revolutionize medicine, speed up the discovery of life-saving drugs, create stronger and lighter materials, improve artificial intelligence, strengthen or even challenge modern cybersecurity, and solve scientific problems that today's computers cannot handle. With its latest announcement, Google placed its Willow quantum processor at the heart of this global competition by demonstrating what it describes as the first truly verifiable quantum advantage, an achievement that other advanced quantum computers can independently repeat and confirm. This marks a major shift from Google's controversial 2019 quantum supremacy claim, which faced criticism over verification and reproducibility. Quantum echoes changes that by introducing a clear benchmark, independent researchers can test themselves. Rather than asking scientists to simply trust its findings, Google has opened the door for scrutiny, replication, and improvement. In science, breakthroughs gain lasting value when others can independently verify them. The achievement also signals that quantum computing is steadily moving beyond theory and closer to solving real-world problems. Google showed that the quantum echoes algorithm can accurately study the structure and behavior of molecules, a capability that could dramatically speed up the development of new medicines, advanced batteries, cleaner energy technologies, and innovative materials with properties never seen before. Researchers also believe the same methods could help explain some of the most mysterious phenomena in physics, from the behavior of powerful magnets to the strange environments surrounding black holes. These possibilities suggest that quantum computers may eventually become indispensable scientific tools rather than experimental machines confined to research laboratories. Perhaps most importantly, this breakthrough strengthens Google's position in the increasingly competitive quantum computing race. Alongside other leading organizations pursuing the same goal, Google has demonstrated that its progress extends well beyond setting speed records. Its hardware and algorithms are beginning to deliver scientifically meaningful results with genuine practical value. Although fully fault-tolerant quantum computers capable of solving everyday problems remain several years away, quantum echoes represents a crucial step toward that future, bringing humanity closer to a new era in which quantum machines tackle challenges that even the world's fastest classical supercomputers cannot efficiently solve. So, what is the computer made of? What does it look like? What was it intended for? Stay with us. Google's coldest computer ever built, Google's Willow quantum computer, is nothing like the computers most people imagine. No computer screens are glowing with information, no keyboards waiting for someone to type, and no loud fans humming in the background. Hidden inside a tightly secured laboratory in Santa Barbara, California, Willow looks more like a futuristic scientific sculpture than a machine built for calculations. Suspended from the ceiling, it resembles a shining golden chandelier made of carefully stacked metal plates. Thick black cables hang from every level, leading deep into a massive cooling system that is just as extraordinary as the computer itself. About the size of an oil barrel, this refrigerator is filled with liquid helium that chills the quantum processor to an almost unimaginable temperature, just 1/1000th of a degree above absolute zero. That makes Willow one of the coldest places ever created, colder than the empty darkness of outer space. Every part of its unusual design exists for one reason: to protect the incredibly delicate quantum states that make this revolutionary technology possible. At the heart of the machine lies Google's remarkable Willow quantum chip. Unlike ordinary computers that process information using bits, which can only be either a 0 or a 1, Willow relies on quantum bits, known as qubits. These qubits follow the strange laws of quantum physics and can exist in several states at the same time. This unique ability allows the computer to explore countless possible solutions simultaneously, instead of checking them one after another. As a result, Willow has the potential to solve certain highly complex scientific problems that would overwhelm even the world's fastest supercomputers. One of Willow's greatest achievements is not simply its speed, but its reliability. Quantum computers are incredibly sensitive, and even the tiniest vibration, temperature change, or electrical disturbance can introduce errors into their calculations. For years, scientists have struggled with this challenge. Google's engineers believe Willow represents a major breakthrough because its advanced error correction system showed something many researchers had hoped for but had not fully demonstrated: that increasing the number of qubits can actually reduce errors instead of creating more. If this approach continues to succeed, it could bring the world much closer to building large-scale quantum computers that scientists can depend on. Despite all the excitement, Willow is not designed to replace the laptop or smartphone sitting on your desk. It is a specialized research machine created to tackle problems that are far beyond the reach of today's conventional computers. Scientists believe future generations of quantum computers could revolutionize fields such as drug discovery, advanced materials, battery technology, artificial intelligence, financial modeling, and cybersecurity. Although widespread commercial use is still years away, Willow already represents one of the biggest milestones in the history of computing. A remarkable blend of groundbreaking engineering, extreme cooling technology, and quantum science that is beginning to make the once impossible seem within reach. But was there really a need for a different kind of proof? Are there possibly any available alternative proofs? Keep watching. From faith to scientific proof. For years, the quantum computing world struggled with the same frustrating problem. Many of the most impressive breakthroughs looked almost impossible to prove. Google's famous Sycamore processor, for example, produced enormous collections of random-looking numbers that were said to be beyond the reach of ordinary computers. Supporters celebrated the achievement as a historic milestone, while critics questioned whether the results truly demonstrated what was being claimed. Because the outputs appeared random, there was no simple way for most researchers to check them independently. In many ways, accepting the results required a leap of faith. That raised a much bigger question. What if a quantum computer could produce something far more meaningful than a sea of random data? What if, instead of generating outputs that only a handful of experts could analyze, it could produce a single answer that another quantum computer could independently verify? Such a breakthrough would change everything. This simple but powerful idea became the foundation of an approach Google later called quantum echoes. While many people focused on how much faster the new method might be, its greatest importance lay somewhere else entirely. It was not just about speed. It was about trust. A result that only one machine can produce is difficult for the scientific community to accept with complete confidence. But a result that another high-quality quantum computer can reproduce becomes something entirely different. It transforms a private claim into a public fact that others can examine, test, and confirm for themselves. That difference is more important than it may first appear. Science advances through evidence that others can verify. Without independent confirmation, even the most exciting discovery remains open to doubt. With verification, however, confidence grows, debates become clearer, and new discoveries can be built on a stronger foundation. The technology industry had already learned this lesson through experience. Over the years, countless breakthroughs that once seemed impossible gradually lost some of their impact as classical computers became more powerful. Clever new algorithms appeared. Better storage methods were invented. Tasks that once looked completely out of reach slowly became merely difficult rather than impossible. Claims that once sounded revolutionary became less convincing as technology continued to evolve. That is exactly why researchers realized they needed a different kind of proof. Instead of asking the world to simply believe extraordinary claims, they wanted to provide evidence that others could inspect, repeat, and verify. Quantum echoes represented a major step toward that goal, offering not just faster computing, but a future where quantum breakthroughs could earn trust through independent confirmation rather than faith alone. So, what kind of structure can contain the quantum computer? What mechanism does the quantum machine operate with? Stay tuned. The room full of wind chimes and the idea of an echo. Google's new quantum echoes method is built on an idea that sounds surprisingly simple. Imagine standing in a room filled with dozens of wind chimes, all connected by invisible strings. You strike just one chime, and within seconds its vibrations travel through the hidden connections, causing every other chime to shake. Before long, the original sound has spread so completely that there is no easy way to tell where it began. Quantum information behaves in much the same way. Instead of staying in one place, it quickly spreads throughout a quantum system until its original path becomes almost impossible to follow. Google's researchers decided to take advantage of this strange behavior. First, they deliberately scrambled the quantum information, allowing it to spread across the entire system. Then they gave just one tiny quantum bit, or qubit, a very small push, so small that it barely disturbed the system. After that, they carefully reversed the entire process, almost like rewinding a movie back to the beginning. If the laws of quantum physics are correct, that tiny disturbance doesn't disappear completely. Instead, it leaves behind a faint signal, or what scientists call a quantum echo, revealing clues about how the information traveled through the system. To detect this almost invisible echo, researchers use a mathematical measurement called the out-of-time order correlator, better known as the OTOC. This value tells scientists just how thoroughly the information has been mixed and scrambled. Interestingly, OTOCs are not a brand new invention. They were first introduced back in 1969 to help scientists understand superconductors. Decades later, around 2015, physicists realized that the very same tool could also explain one of the universe's greatest mysteries: how black holes scramble information that falls into them. Google pushed the idea even further. Instead of performing the scrambling and reversing process once, the team repeated it a second time. This created an even weaker and more delicate signal known as OTOC squared. Although the echo became much harder to detect, it also became dramatically harder for even the world's most powerful classical supercomputers to reproduce accurately. That improvement solved one of the biggest criticisms of Google's famous 2019 Sycamore experiment. Unlike the earlier test, which produced random results that outsiders struggled to verify, quantum echoes generates one clear, measurable value. Other advanced quantum computers can independently repeat the experiment and compare their results. That makes Google's latest achievement not only more convincing, but also far easier for the scientific community to verify, strengthening the evidence that quantum computers are beginning to outperform classical machines on carefully chosen tasks. What is the talk on Willow all about? How does it contribute to the quantum computer? Stay glued. They tried to disprove everything. Google's astonishing quantum computing breakthrough wasn't based on a lucky experiment or a bold claim. It was built on an overwhelming mountain of evidence collected with extraordinary care. Before the company's scientists were willing to trust what they were seeing, they gathered nearly 1 trillion individual measurements. To put that into perspective, if you counted 1 second at a time without ever stopping, it would take roughly 31,000 years to reach the same number. This enormous amount of data gave the researchers confidence that the strange quantum signal they observed was real and not simply random noise or a statistical accident. Every result had to survive countless rounds of testing before anyone dared to call it a breakthrough. At the heart of this achievement was Willow, Google's powerful 105-qubit superconducting quantum chip. Unlike its earlier quantum processor, Sycamore, Willow was designed with much greater precision and stability. Its qubits could remain in their fragile quantum state for longer periods, allowing the chip to carry out much deeper and more complicated calculations before errors could build up. It also achieved remarkably low error rates, making it one of the most reliable quantum processors Google had ever built. Interestingly, Only 65 of Willow's 105 qubits were actively involved in the experiment, while the remaining qubits either stayed idle or monitored the process to ensure everything was working as expected. To understand just how impressive Willow's performance was, Google compared it with Frontier, one of the fastest classical supercomputers ever built. The difference was nothing short of astonishing. A calculation that Frontier would need around 150 years to complete was finished by Willow in only a few hours. For that particular problem, the quantum chip performed roughly 13,000 times faster, highlighting the enormous potential of quantum technology when applied to the right kinds of tasks. Still, Google knew that extraordinary claims require extraordinary proof. Rather than rushing to celebrate, its scientists tried as hard as possible to prove themselves wrong. They launched an intense internal red team review, challenging every assumption and searching for flaws in their own work. The team compared the results with 9 different classical computing methods and devoted the equivalent of 10 person-years of careful analysis before finally publishing the research. The project also carried additional weight because it involved Michel Devoret, Google's chief quantum hardware scientist and a 2025 Nobel Prize winner, whose pioneering research helped create the transmon qubits that power Willow. Even after surviving this relentless internal examination, Google's researchers knew their work faced one final and perhaps even tougher challenge. The wider scientific community would now carefully inspect every detail, repeat the experiments, and attempt to verify the results. Only if independent experts reached the same conclusions would this remarkable achievement truly earn its place as one of the most important milestones in the history of quantum computing. How exactly was this machine born? What materials are contained in what has led into today's quantum computer? Stay with us. From a laboratory number to the structure of real molecules. The latest breakthrough answered one exciting question, but it immediately raised an even bigger one. It is impressive for a quantum computer to outperform one of the world's fastest supercomputers, but does that achievement actually matter outside the laboratory? Can all that incredible speed help scientists solve real problems, discover new medicines, or design better materials? Or is it simply an extraordinary technical demonstration with little practical value? That was the challenge Google and a team of researchers from the University of California, Berkeley decided to tackle. Instead of giving their quantum system an abstract mathematical puzzle, they asked it to study something from the real world. Using the quantum echoes algorithm, they analyzed 2 familiar molecules. One was toluene, made up of 15 atoms, while the other was a larger and more complex molecule known as 3,5-dimethylbiphenyl, containing 28 atoms. These molecules were not chosen by chance. Scientists have spent decades studying them, meaning their structures were already well understood. That gave researchers a reliable way to compare the quantum computer's answers with results that chemists had trusted for years. To understand why this mattered, it helps to look at one of chemistry's most powerful tools, nuclear magnetic resonance, or NMR. This is the same basic science behind MRI scanners used in hospitals. Instead of taking photographs of molecules, NMR allows chemists to uncover their hidden structure by studying how their atoms behave in magnetic fields. Interestingly, history has now come full circle. More than 25 years ago, some of the earliest quantum computing experiments were performed using tiny magnetic properties inside liquid molecules examined with NMR machines. Today, the roles have completely reversed. Instead of molecules helping scientists build quantum computers are now helping scientists understand molecules. The results surprised even experienced scientists. Google's quantum computer delivered measurements that closely matched decades of trusted nuclear magnetic resonance (NMR) research, proving it was capturing real physical information instead of producing random or unreliable data. But that was only the beginning. The new approach also revealed hidden connections and precise distances between atoms that conventional NMR techniques often miss or struggle to measure. That breakthrough could transform the way scientists study molecules. According to Berkeley chemist Ashok Ajoy, combining quantum computing with NMR could dramatically strengthen one of chemistry's most valuable research tools, speeding up the search for life-saving medicines, improving our understanding of complex molecules, and helping researchers develop stronger, smarter, and more advanced materials than ever before. Even so, there is still a long road ahead. The molecules studied in this experiment were relatively small and required only 15 qubits to analyze. Google's long-term goal is far more ambitious, tackling molecules roughly 4 times larger, a challenge that would push beyond the limits of today's classical computers. Reaching that milestone will require solving an entirely different set of scientific and engineering problems, and it is exactly the kind of claim that experts around the world are already eager to examine closely. But did people really believe the claims of quantum? Were skeptics able to prove them wrong? Let's find out. The skeptics, the hunt for a shortcut, and the claim that survived. Google's announcement that its quantum computer achieved a 13,000-fold advantage over traditional computing immediately captured the world's attention. To some scientists, it marked a historic turning point that could reshape the future of technology. To others, however, it raised an equally important question. Has quantum computing truly pulled ahead? Or is this another breakthrough that classical computers will eventually catch up with? That debate is now at the center of one of the most closely watched scientific discussions in recent years. The excitement surrounding Google's quantum computer comes with one major question that scientists still cannot answer. Yes, the machine solved a difficult problem far faster than any known traditional computer could. But does that mean quantum computers have permanently taken the lead? Not necessarily. Critics argue that a breakthrough classical algorithm could appear at any time and dramatically change the picture. History has shown this before. Problems once believed to require enormous computing power suddenly became much easier after researchers discovered smarter, more efficient methods. Because of this, many experts urge caution. They believe it is still too soon to celebrate a lasting victory for quantum computing, since tomorrow's mathematical breakthrough could completely reshape today's understanding of what classical computers can achieve. Others point out that proving a scientific achievement is very different from building technology that people and businesses can actually use every day. Google's experiment may represent an important milestone, but practical quantum computers capable of transforming medicine, finance, cybersecurity, and artificial intelligence are still likely years away. In other words, the science may be advancing rapidly, but real-world applications still have a long journey ahead. There is another important detail that many headlines overlooked. Google's impressive comparison was made against one of the most advanced classical simulation techniques available today, known as tensor networks. It was never intended to represent every possible classical computing strategy. To test Google's claim even further, researchers developed improved tensor network methods, including a sophisticated approach called belief propagation. Even with those improvements, they still could not realistically recreate Google's quantum echoes experiment at its full scale. MIT physicist Aram Harrow offered one of the most balanced opinions in the debate. He explained that matching Google's results with classical computers would probably require not only enormous computing power, but also a completely new algorithmic breakthrough, one that simply does not exist today. That leaves the scientific community in an intriguing position. Experience reminds researchers to remain cautious because classical computing has surprised the world before. Yet, despite months of intense examination and repeated attempts to challenge Google's findings, no hidden shortcut has been discovered. For now, Google's remarkable achievement has survived its first major wave of scrutiny, strengthening the possibility that quantum computers may finally be solving problems that today's most powerful classical computers can no longer handle in any practical way. What could be the origin of quantum computers? What are its limits? What areas need to be worked on if they really want to control the tech world? Keep watching. The secret behind Willow's breakthrough. Google's Willow quantum computer has achieved something that many scientists once believed was still years away. Its latest breakthrough is not just about building a faster computer. It is about using one of the strangest and most powerful ideas in modern physics to solve problems in an entirely new way. At the heart of this achievement is a mathematical tool known as the out-of-time order correlator, or OTOC. Although its name sounds complicated, its purpose is surprisingly simple. It helps scientists track how information spreads, mixes, and becomes almost impossible to untangle inside quantum systems. What makes this discovery truly fascinating is where this same mathematical tool has appeared before. The very equation Willow used to study the movement of information inside chemical systems is also one of the main tools physicists use to understand black holes. These mysterious objects are believed to scramble information faster than almost anything else in the universe. In 2015, researchers proved that nature has a maximum speed for this kind of information scrambling. According to our best theories, black holes operate right at that ultimate limit. Even more astonishing was what scientists discovered next. As researchers explored the strange world of quantum physics, they found that certain chemical reactions behave in ways that come surprisingly close to the same mathematical limit once thought to describe only black holes. At first glance, these three things could not seem more different. Black holes are gigantic objects hidden deep in space. Molecules are unimaginably tiny building blocks of matter. Quantum computers are advanced machines created by human engineers. Yet, through a powerful mathematical tool known as the out-of-time ordered correlator, OTOC, scientists can describe the behavior of all three using the very same equations. First proposed in the 1960s, this little-known idea remained largely overlooked for decades. Today, however, it has become a vital tool across many fields, including superconductivity, chemistry, string theory, black hole physics, and cutting-edge quantum computing, revealing unexpected connections between some of nature's most mysterious phenomena. Willow's success did not stop there. The chip also demonstrated a major improvement in quantum error correction, one of the biggest challenges preventing quantum computers from becoming practical. By reducing errors more effectively than before, Google has taken another significant step toward building reliable quantum machines capable of tackling problems beyond the reach of today's supercomputers. Although only a small number of researchers can currently access Willow, its results have already attracted worldwide attention. The system appears to outperform the best-known classical computing methods on certain tasks, and its findings can potentially be checked by other advanced quantum computers. Whether this breakthrough eventually leads to life-saving medicines, a deeper understanding of black holes, revolutionary materials, or even more powerful computing technologies, Willow has already changed the conversation. It has shown that quantum computers are no longer just exciting theories. They are beginning to solve real problems that classical computers simply cannot handle, marking a historic turning point in the future of science and technology. So, what do you think about the latest achievement of Google's quantum computer? Could there possibly be someone who will challenge their authority? We'd love to hear your opinions in the comments below. And don't forget to like and subscribe.